Right? Let's just assume that's correct. Okay, so I don't think anybody's going to join us long, but there may be other people who will come in person. So today we were going to discuss these, try to discuss Hasse diagrams. I just wanted to say a little bit about, and then we can try to do some examples. To be the Higgs boson. We can try to get some synergy between this and the Coulomb branch results. Because there's a little bit of subtleties. So these are Higgs branch. Unitary. Basically, the point is that there's these key things that we need to define. So given a quiver, remember how we were drawing that, so we could have one. Let's do something simpler. Let's do it like this. Projective space example. So given a quiver, maybe I'll put I'll put a little bit more. So given a quiver, so we will then we define the Cartan matrix. And so the Cartan matrix, so first of all, I should say that there's also this equivalence. So we can unframe, we discussed before. We can get one. Right? So so we have the Cartan matrix. So we're going to have so it's going to be well, I'll just write it this way. 2 times identity minus the adjacency matrix. This is for the non-numeric quiver, so we can't, it's not a priori. These are simply based. I think there is some ways of doing Nakajima quiver rays with the non-simply base, but that's much harder. Whereas in the Coulomb branch case, it's much easier, I guess, so in some sense. Well, much maybe for you, for mathematicians, it's still not so easy, but there is a definition at least. This definition of Nakajima and Weeks. So, all right, so we got that. That's a Cartan matrix. So in the example, with the unframed, we're going to have well, 2s on the diagonal because there's no loops. There were loops. So I have to say this is a little bit. This would be for the this would be for the in the case with loops. We put it in here 2 times the number of loops. So I'm doing undirected graph, but another way to say this would be you would take a directed graph and then you would just double the graph. And you put arrows in both directions, and then you would have 2 loops at a vertex. Okay. So now we're going to have 2, we're going to have minus n. minus n, and here minus 1, 0. Right? And this is saying that we have part 10 pairing. So we're going to have E1 with E1, EI with EI is 2. E1 with E2 is equal to minus n, which is E2. E1 with E3 is 0. This is symmetric. I'm just writing it out to put the answer. Okay, so that's a Cartan pairing, and then we have dimension vector. So we have 2, 1 in the frame case. We don't include the frame case. We don't include so for the frame case, it's going to be 2, 1 and 0 for the gauge frame. Or then we just get the 1 on the frame. Okay. And if we want to do the Cartan matrix for the frame case, we would just use only the gauge. That's the setup. And with just this information, Gwyn has a computer program which will then generate the Hasse diagram. You just give it the Cartan matrix, you send it to me, the Cartan matrix and the dimension vector.
So the thing here is like everything, so that's the base, and we only do the loops. So we don't have both some anti-symmetrics. So the loop is a joint.
Right. The loop is an adjoint. You can have as many copies of it as you want, as many loops as you have. But the thing is that here, where the groups are unitary groups, they're not specially unitary. So adjoint is just, you could also think of adjoint as tensor product of fundamental with its dual.
There was some problem with the code with
Yes.
Yeah, someone pointed out it was a problem. They said they get it corrected, but he wasn't sure if it's completely correct.
So it's So it's Marcus actually. So because running a quiver, we have the product from the cover with this mechanism. Maybe I can.
Yeah, maybe you can show it. So there is this is a common throwaway, but maybe it's more complicated than the common throwaway you have in mind. But I can tell you about how to do this common throwaway. Well, you could just tell me your way. Okay. So maybe I just tell you briefly about how this program is doing it. So so we're going to have a paper at some point, but we're going to explain this mathematically. But basically, the point is that we have this set sigma. So you can have parameters. Doesn't really matter. So it's the set of. So we're going to have a. So for the quiver, gives rise to some positive roots. The root system. So I can tell you what they are, but let's just say that we know what the roots are. So this includes the real roots. That means that alpha is 2. The imaginary, which means that alpha is less or equal to 0. So these are some. This quiver gives you this root system, and we are interested. We care about the alpha in R plus with alpha less than or equal to the dimension vector. So the ones that were bigger than the dimension vector aren't going to. This means i.e. So let's call it dimension vector v, i.e. alpha I is equal to v and I for all the coordinates. It's not, and there it won't play a role in there. And then this set is going to be a set of alpha and this positive root space such that for all alpha equal to R1. Actually, I think they can just do that says alpha 1. Alpha 5. Then we have that this dimension P of alpha is strictly greater than P of alpha 1. So this is the expected dimension. One minus a half. Expected dimension. I.e. we take the sum of these the sum over all arrows. The arrows. Let's say A is going from I to J, so we have an arrow. Let's do this for the let's let Q be the double quiver.
So this is the formula which counts the hyperbolas and
Right. So for each line, we're going to make it arrows going both ways. Now we're going to have a sum over all arrows, I going to J of, we're going to have a dimension at I, the dimension J, so this is equal to the dimension of C to the alpha I, C to the alpha J. So we're going to have this guy, that'll be the dimension of this space that we're trying to take the reduction of. And then we're going to subtract the dimension of the group that we're taking the quotient by, which will be the sum over all vertices. These are the vertices of the dimension alpha I squared. Right, so we can take all of that. It'll be the dimension of the general linear groups of each of the vertices or the unitary groups. We're going to take twice because we're doing symplectic reduction. Right? But actually, it's actually really the quiver variety. Let me just put this 0, 0 out there. I don't have enough room to say that whole thing. Yeah. So this M00 Q alpha is going to be defined as the sum C alpha I C alpha J modulo Hamilton reduction PGL L. This is the general linear, this is the product of the general linear groups mod and overall scaling. So because of that, we're not subtracting just the sum dimension of the general linear group, but also added to. So
So I,
that's the install
exactly.
so here, I mean, you know, so for example, we have U with a lot of groups. And also we have, like I say, we have two rivers. So one is U with some group, another is U, it's N with U with some group, but connecting to another one. But these two have the same structure. And
So which quivers?
so when you get a circle of N.
Circle of N.
Yes.
Like the N vertices.
Yeah. No, just one word is the reference.
One node of N.
Yeah, one node of N with many loops.
Many loops. Okay.
Yeah, let's say G loops.
Okay.
Yeah, and and another is like so yeah, this is a quiver one, and quiver two is you already take the same thing, but then you connect this with a node of one.
Right, yeah,
Yeah, so these two have the same expression actually.
right.
So then this division formula not applies to the first one.
I said expected dimension, I didn't say it's actually the dimension all the time. I only said it was expected dimension,
Ah,
I didn't say it was actually the dimension every time.
As we,
It's very important, that it's an expected dimension enough. So the whole point of this set here is to tell you when the dimension, it's actually something a little bit stronger than saying that the dimension is equal to the expected dimension. It's saying not only is the dimension equal to expected dimension, but that for all of the decompositions of alpha into smaller dimension vectors, you get a smaller dimension. So that means that, so maybe we come back to this example. Did you want me to say anything about it now, or just you wanted to tell it? I just wanted to say that, so then the proposition, maybe, maybe I should sell it here, but this is Coley-Bovey. Make sure I don't have anybody online. No, okay, so I don't have to worry about questions. But the Coley-Bovey is that, alpha is in sigma 0, 0, if and only if there exists a simple representation of the projective algebra 0. After 0, okay, of dimension alpha. So in this case, the dimension of M is actually equal to the expected dimension. It's twice. Okay. So yeah, so what should I say about it? Yeah, I don't want to go into too much detail, but somehow let's go to your example. Let's see what happens there. Let's do it like that. So we have this n, these loops. Now we're gonna add a 1. So now we're gonna let alpha be equal to n1. But it's quiver. Simply the quiver. If we wanted to double it, we would have been. Sometimes I put the Q bar for the double quiver. We'll do that. The double quiver. So now we can have this Q bar. Now we have 2G, but we're doubling. Okay, so anyway, alpha is n1, and now we can have a decomposition of alpha into n0 plus 0, 1. Alpha is the dimension vector. So now so now you're telling me that it's the isomorphic. Is that true though? For this example, for general n and g, you're saying it's isomorphic if we add the 1 on or not?
is it really,
the singular part is the same.
Ah. Um. Okay. Might be. But anyway, this is not gonna, this is actually going to be in sigma here, right? Because so what's gonna happen here? E of alpha is going to be equal to, so the Cartan matrix here is going to be 2 minus 2G, 2 minus 1 minus 1. So P of alpha, it's going to be n squared 2 minus 2G plus 2 here minus this 2n. Right, this if we take this sum, and then we're gonna take 1 minus a half of this. Right, but now you see that this is going to be greater than P of just n0 itself plus P of 0, 1. P of 0, 1, this is 0. But P of n0, unless n is at most 1, this is going to be that. So this is still going to be in sigma. So it's still going to have the correct expected dimension. But what you're telling me is that there's a minimal leaf here, which is true. We have loops here, so we have minimal leaves. The minimal, that was true before we added this on as well. The minimal leaf will be, we just have just the direct sum of the symbols, right? It's going to correspond to n times d1 plus d2. There's decomposition where we have n copies of this one-dimensional presentation here and 1 copy here, but the one-dimensional presentations here are 2G dimensional space of one-dimensional presentations, but you have 2G loops there. So this, instead of this minimal leaf, when you have no loops, the minimal leaf has dimension 0.
So why is one?
Well, one-dimensional representation. So, okay, so I didn't give you the interpretation in terms of representation. Should I say it? Do I need to say? This is sort of the mathematical part of it. Yeah. Take a picture or erase in case anybody needs this later. Oops. Okay. I leave out the dimension, the definition of this, and I erase the rest. So, but here is the representation, theoretic interpretation. So basically, so given a quiver, we're going to put arrows in, we're going to direct it. It's important for this purpose to be directed in general. But given some quiver, I'm going to loop there. I'm going to put the dimension vector to 1, 2, 1. We associate the system of linear maps. So we're going to have C1 going C2 going to C1. So we're looking at we're going to look at assignments to these arrows. So we're going to call this arrow, let's say, let's call this arrow A1, A2, A3. So representation of the quiver of dimension alpha, so it's going to be alpha here. This dimension vector is a row inside of with the C1 the C2 is gonna be, row, the thing, so, but it's, the row is gonna be equal to row A1, gonna be here, plus, C2 to C2, inside of here, we're gonna have row of A2, plus, C1 to C2, we're gonna have row of A2. So if I call it arrows, AIs, then row representation sends each arrow to a linear transformation. You could more generally, instead of having vector spaces CIs, you could just have vector spaces VIs. You don't have to consider them to be the standard vector spaces. But for the purposes of the variety, it doesn't matter. And then definition. That so we have a linear transformation from row 1 to row 2 is the system is T, so TI. But now maybe I should better call these vertices something, so let's call this V1, V2, and V3 for the vertices. That's gonna be TI is going from VI to VI, such that row 1, an arrow, circle TI is equal to TJ, circle row 2 of the arrow, where the arrow is going from I to the vertex. These are the vertex 1, vertex 2, vertex 3 here. Okay, so that's a homomorphism. And then an isomorphism is if the T is TI. Okay. So now. Right. So we can do this example again. Well, okay, maybe I read this up here. Didn't want to. Oh, so. Now the point is that this quotient here. This is representing, this guy representing all representations of dimension alpha. It's summing over all arrows in this common space. And this guy is representing isomorphism. So this is the group of change of bases. Up to scaling. And overall scaling. So that's the group that acts on these. So if you have an isomorphism, it's given by some T, which will be in here. So T modulo scalar will be in here. But since we're always conjugating by the T, if T is a scalar, then it will automatically, it will not be anything. So if you multiply Ti and Tj by the same scalar, this identity will still be satisfied. And so in other words, if Ti and Tj are all equal to the same scalar, we just get that row 1 equals row 2. So the action is trivial. So the action is by this PGL alpha. So this is the modular space. This is the upshot is that this is the so if we had a single quotient, this would be just the moduli space of reps up to isomorphism. Yeah, we take the ordinary symplectic quotient. If we take the symplectic quotient the symplectic quotient, this J in Q1 bar, the double guy, we take its symplectic quotient at PGL alpha. Symplectic quotient, this is defined as mu inverse of 0, ordinary quotient, so this is ordinary. When I do 2 slashes, it's ordinary, uses 3 slashes, it's symplectic. We take the ordinary quotient at PGL alpha, we have this condition at the moment now. Momentum is 0. And the momentum, we've seen this formula before, I don't remember what it meant, we saw it before, but mu of rho is equal to the sum for all arrows in the undoubled cover of rho of A star, minus rho of A star, rho of A star, it's the reverse arrow. So here, if we were to write in the other ones, the A1 star, right? Yes.
So why am I not talking like this? If it is more, it's a why?
Well, it's basically, or I understand it. You might understand it better than I do. There to prove that there's this equivalence between symmetries and conserved quantity, right? And so like when you have angular rotation, you have this angular momentum, which is a preserved quantity. But for any symmetry, in this case, the symmetries is PGL alpha. And so this mu is giving you the associated momentum, associated conserved quantity, and you can compute it just given by this formula. Because you're taking change of basis, you're taking conjugation by matrix. And now you're in some sense differentiating that this commutator. That makes sense.
It is the way.
I'm trying to speak physics here, but if I say the wrong words, you have to tell me. So, but the nice thing is that so it's a proposition. If X is a smooth symplectic manifold, and G acts on X in a Hamiltonian way, meaning it has a moment. Not every action on the symplectic manifold had a moment map, i.e. exists this mu for it. And I could give you a mathematical definition of mu if you like. Although, in the case at hand, we're only dealing with X being cotangent bundle of something on which G is acting, so then you can just write down a formula for mu. So if you're a cotangent bundle, mu always exists, and it's given by a particular nice formula, which looks like this. And if you're not a cotangent bundle, then it doesn't have to exist, but it can.
So when you have the answer in the problem, there is a condition in the moment, right? That
You mean this moment map, it's mu versus 0, you mean? Yeah, we always use that.
they must be in the non-vector. Null space.
Oh, okay, yes. This null space of Cartan matrix. So there's a couple of things. In general, the Cartan matrix doesn't have a kernel, doesn't have to have a kernel. It's like for these Dynkin cases, it doesn't have. For extended Dynkin, it does have. But there's another thing, and that is that when we look at, like, for example, stability condition, we want it to have 0 pairing under Cartan form with the dimension. You could also do. So, but we can try to figure out.
So that's the condition.
We can try to figure out what you're thinking. So that's if you want to vary stability, the state, and the reason for that is that we're really, for an ordinary variety, if we were not, if we wanted to get rid of the P here, then mathematically, either you get the same thing or you get a stack, which is a little bit slightly more complicated. But you don't want to deal with stacks, you want to deal just with ordinary varieties. You should really put a P here. Because you're putting a PGL alpha, actually, that means that we need to be using everything modular. These groups, GL alphas are always modular scalars. So actually the stability parameter, so in general, I'll just say something very quickly. So note. This is unrelated to what I was about to say, but maybe I finish the statement and then so otherwise no one will follow anything. So if you have this and Gx freely, so nice action freely and properly, then this Hamiltonian reduction is also smooth. So we're not in this situation. We're dealing with singular things, but we're somehow not that far from the situation. Okay, now I say what I was just saying. How many times? That is that given any not necessarily symplectic quotient x mod g, we can consider variation of GIT. Probably will want G to be reductive for this. And it's just given by x mod theta, G plus theta, there's some character. Like this one. And then as I said, this is considered to be called a stability condition. But now, of course, if G is PGL alpha instead of GL alpha, then your characters. So for GLN, there's a single character; it's a determinant, right? So GLN, the check, which is this OMS as a group, and GLN to C cross is just Z, which is given by the determinant. But if you have PGLNs, the PGL of so you take a product of GLNs of mod by C cross, then instead of getting a Z at every vertex, you get a Z at all the vertices minus 1. So you get 1 less, right? Because of this modding by the scalar. So now PGL alpha check is then I can over to Z to the Q0 mod Z. You have to kill off the Z. And this mod Z is actually the way we actually do it. It's not mod Z. We take it as actually as this dimension vector curve inside of Z. That's where the perpendicular comes in. If we take PGL alpha characters on PGL alpha, because PGL was a quotient of GL. So then the characters to be thought of as a subspace of all the characters, the ones that descend to the quotient. So it's a perpendicular to the dimension vector. So this is why the perpendicular to dimension vector enters in the unframed case, as Amihai was saying. In the framed case, this is not an issue, because in the framed case, instead of using PGL, you use GL. So this is for the unframed case. If you want to do framed case, you can get rid of the P.
What's the large function?
Variation of geometric invariant theory. This was Mumford, Mumford defined and studied this geometric invariant theory. Okay. I think I erased some things I shouldn't have. I should take a picture as well. So I have said many things. Oh, it's too fast. All right, so is everybody with me here? Is there anything that I should verify? So I'm just trying to explain some aspects of the, I was really trying to think of some aspects of the Hasse diagram, but in order to really understand from the mathematician's point of view, at least from my point of view, what the Hasse diagram is giving you in this case, it's helpful to know about this language of representations. In other words, for a physicist, perhaps you're happy with this symplectic quotient, or maybe you call it a hypercalar quotient. You're happy with that, and then you're happy looking at the different way of looking at the stratification. You get a bit that's not going to be smoothed down and have these leaves, right? Perhaps you're happy with that, right? From a mathematician's point of view, this is a particularly nice object. So in mathematics, you can consider these quotients all the time. Like there's lots of examples where you can consider quotients like this one, JT quotients, but only in certain special cases, and probably a lot of the cases we care about, but only very particular quotients like this are going to be moduli spaces. That means that you're defining some type of object and looking at a space that parameterizes those objects up to isomorphism. And that's what's happening here. This isn't just a hypercalar quotient. Actually, every point in here is a representation. It's some linear algebraic gadget. And the space is parameterizing all of them up to isomorphism, but not just all of them, actually, all of them that have momentum 0 up to isomorphism. But saying that it has momentum 0, it's actually equivalent to saying that it's a representation of this thing I call the pre-projective algebra. So pi 0 is defined as the path algebra of the quiver modulo the relation, which is sum of a star minus a star a. In order to define a representation just of the path algebra, it's just a representation of quiver. To define a representation of quotient of an algebra, it has to annihilate the ideal. So the representation has to be 0 on this. And so for the representation to be 0 on that is exactly saying that this moment path is 0. Does that make sense? So we can actually think of, so if it were just saying that we were looking at the moduli of things with momentum 0 on isomorphism, that wouldn't be as nice. But the nice thing is that actually moduli of representation of some algebra of isomorphism. So it's very powerful, but it's true. So this is what we're doing. And now, because of that, when we look at the stratification, one way of thinking about the stratification is as telling you how the representation decomposes the representation. There's two ways of thinking about the stratification. You can think about it as a way that might be more familiar to you based on the stabilizer. So you have a quotient, and you have a point of stratification corresponds quite generally. We have a quotient construction to the locus with the stabilizers conjugate to some given subgroup. This turned out to be equivalent in this case to asking for a condition on how the representation decomposes as either a sum of smaller representations or more generally extension of smaller representations.
Yeah, the first point that has the principle interpretation. Second is
Right, exactly. But it's very powerful. That's why we can do everything so much more easily for Nakajima quiver for the unitary case than for the orthosymplectic case. So orthosymplectic case, that first interpretation is still valid as stabilizer, but the second is not, as far as I know. It's not a moduli of representation. So maybe it is in orthosymplectic case, at least in some orthosymplectic cases, but this has not been studied yet, as far as I know. Yeah.
The difference between each of them.
The difference is, I didn't say, I just said it was some modification that uses it. They didn't say it was give a definition. Yeah, I can give it to you. So, so BGIT, it means, oh. This is the beta semi-stable locus. How to say what it means, so we have X. This is really, the terminology is a little bit confusing here. So X is in X beta, so we have semi-stable, so we have stable. We have semi-stable. Is the most important probably, and we have unstable. But unstable is not defined as not stable, it's defined as not semi-stable. That's a confusing thing. It really should be semi-stable, but that sounds strange. That's called unstable. This is a confusing terminology. Stable is a stronger condition than semi-stable, but unstable means you're not semi-stable. Okay, so X is in X theta semi-stable. If so let's see, I'm just going to, let's let X be, let's let X be affine. So like e.g. Inside of CX or something. Okay. I don't want to deal with the projected case. So X is in theta semi-stable if there exists a function. So functions on X, which is a theta invariant, such that f of X is not zero. So this is the semi-invariance. It means that if I act by an element of the group times such that G star of F for G in the group, then I get the character of G. So if you act by pulling back under this automorphism that you're, so G is acting by automorphisms on X. So given a function, we can get a new function, which is compose it, but pre-compose it with the automorphism. Or the inverse, I can never remember. And so then we call a semi-invariant one, so that if you do that, you just get a multiple of that according to this theta. So of course, if theta is zero, then semi-invariant is just invariant. If theta is the trivial character, which I'm calling zero, or maybe I should call it one, depending on how you want to think about one or zero. If it's a trivial character, then this is just an invariant, but in general, it's a semi-invariant. And so that's the, so of course, the way I define it then, no. By definition, then X0 semi-stable is all of X. Now, this becomes a little bit more complicated if your X is not affine, because then you don't have enough global functions. You need to equip it with a line bundle that's ample, has enough global functions, etc. Then you can do all of this. There's actually some nice notes of Richard Thomas on GIT, so if you're interested in understanding more. Richard Thomas has some notes. Looks right there. So, yeah, he's mostly dealing with the projected case. So that's the one I'm dealing with the affine case here. Okay, so so that's the condition, and so now if X is if theta is zero, we just get X back. But if theta is non-zero, we get an open subset. So now upshot is this X mod theta G can be thought of as, instead of taking the quotient of all of X by you take a quotient of an open subset. And this can produce a much nicer quotient. So So, it's this. Let's give a very quick example of that, the one I often like to give, which is e.g. So mathematically. Using GIT, if we take Cn modulo scaling, so this could be defined as that the space whose functions are the invariant ones. The function invariant are scaling of degree 0 ones. So this is just a point. It's not very nice, but if you take away the origin, you're going to get the projective space of dimension 1 less. And this is also going to be the theta semi-stable locus for some with the correct choice of theta. Right. This is not really related to the situation we're in too much, because the situation we're in is the cotangent bundle over these things. But the situation we're in is much milder in the sense that we don't have quotient that just gives you something which is only a point. Instead, when we vary theta, typically for theta equal to 0, it's still okay. It still has it's some cone, which is nice if you like to study. And if you vary theta, you may get a resolution of the cone. So the same dimension, but smooth. Does that make sense?
So if we go back to the minimal one,
Yeah.
so how do we do that?
Okay, so let's take another picture and ready. I hope this is helpful. But if it's not, let me know. Okay. Because of everything. That was just all sort of the way I'm thinking about it, which is useful. Now there's two different ways. For the unitary case, there's two ways to think about the stratification, but for the general case, there's just one way still to stabilize it, right? But this is very nice because we have this interpretation. But so now, okay, so let's get back to this example. So let's go back to this example. Now the Leos of this affair. So we have the minimal. These are representations decomposing as onto one dimensional since
The minimal you mean a leaf like on the top.
a minimal leaf is the smallest leaf. So you're thinking of like in the nilpotent cone, there's a terminology. You have the regular, which is the open leaf, the subregular, which is the next one, the subregular. I'm not sure if we can do that for a general space. With the open leaf, I'm not sure if I've ever heard of the sub-open
So
leaf.
the meaning minimal like that is
Yes, yeah. Except in the nilpotent cone, actually, usually it's the sub of what you mean. The 0 is usually the minimal leaf. The nilpotent cone. But here I really mean the minimal one, not the next to minimal. What you call minimal really next to minimal because 0 is the minimal. Since it's so obvious, you don't call 0 minimal. Which is fine, we can do the same thing. I have no problem with that, but it's a slight abuse of terminology. But here I really mean the minimal. So that representation decomposing as 1, 0, n copies of that, and 0, 1. Right? So that's the way the dimension vector decomposes. So in general, you could have multiple strata with the same decomposition because it's actually so the strata in general, it's in the node. Stratification. Stratification means a union of views of M0, 0 to alpha in general. Given that it's labeled by multiplexers. So we're gonna write alpha is equal to N1 alpha 1 plus N2. So we're gonna have N1. It's not just a list of roots. But they're going to be with some multiplicities and multiplicities. Okay. And I. So, okay, so in general, I need to know more of this. What the decomposition is, I really want to have the multiplicity, so I'm gonna have, I could have 1 times this plus. So what does the multiplicity mean? I can tell you what the multiplicity means. This means, so the decompositions. V is equal to, well, let's say, the isomorphic to V1 to N1. This is the leaf, the decompositions of like this. So you can have a representation which is isomorphic to some sum of representations. But in this case, the first representation occurs N1 times. So you can have alpha 1 equal to alpha 2, but 2 different representations, V1 and V2, whereas if you instead of alpha 1 plus alpha 2, just have 2 times alpha 1, you have only a single representation occurring twice. So you're specifying that those two are not just the same dimension vector, but actually isomorphic to each other. That makes sense? So this is the decomposition. So if I write it this way, this will have this decomposition. In general, we could have a smaller leaf. We could have a smaller leaf like N times 1, 0, for example. This would be really the smallest one ought to be this one. We have only 2 representations, one dimension 1, 0, one in dimension 0, 1. But actually in this case, if we look at this possibly larger leaf, its closure is already smooth. So this is the leaf. So this one defines a leaf, and something. This one does not actually define a leaf, and that defines a subset, which is not a leaf. No, it's not that. It's just that it's just that it's the reason for it. It's just that no, okay, I think I said something wrong. Sorry. So this is. No, the problem. Okay, so what I said would be true of n equal to 1. Sorry, this was this one. So there's a case in which
It's like something that's about
It's not. This is actually. Let me show you.
K and
Kn. Okay, we'll get back to this.
Okay.
So the
K1 with multiplicity.
Yeah, let me just say what this is there here first. So what does this lead mean? So a representation C 0, 2G. This there is just 2G copies. The representation is just C. The representations form just a copy of C to the 2D. You have to choose what all these arrows are for each one-dimensional transformation. So we get, and then we take 0 as C, then the representations here are just only the 0 representation. Because you have a transformation between 0 and C. That's 0. So in this case, this is isomorphic to C to 2G. Okay, now that's yes, so that's the point. We have this n here, which is not equal to 1. So right. Okay, so there's another thing you can do, which we'll talk about in a second. So it becomes slightly more complicated. What I was confused about, what I was saying when we're trying to say before, there's a slight confusion that you also have. We're using GLN here, we could be using SLN here. So this, and we'll say something about that in a second. What was the KN you wanted to do?
K1, then big multiplicity.
Multiplicity N, see? Electronic or quiver, okay. So Amihai, this is actually not so the simple quiver, but the point is that loops create an additional complication that we're going to avoid. You have to be careful when I talk about the loops. So we're going to do it like that. This is a little bit easier. So I'll get back to that. There's a no. Here. One also. And right. The whole, so this is what I was going to say before, is M00 as a product. C2G. Some smaller. So it's not just at the minimal leaf, it's C2G, but actually the whole thing is globally a product. Okay, but so now let's do this again. This won't happen here. This happens, the minimal leaf is not 0. This happens because we have loop. With no loops, the minimal leaf will now be just 0 again. Okay, so now minimal leaf. It's going to be again K times 1 0 plus 0 1. And now the dimension is 0 because when only one dimension vector is 1, only one vertex at dimension 1, the other is dimension 0, with no loops. There's nothing you can do. You just get dimension 0. This is always true. For minimal. And this product, by the way, is also always true when you have loops. So when you have loops, basically the only way in which it fails to have minimal leaf, which is just a point, a vertex, is because you're globally a product of something that is having that property. Okay, so now let's do the other loops. So we can have we have to look at the dimension vector. So we can have also after that. There's two different things we can incorporate the one. We can incorporate the one into something. We can have and one. The other, so general. Let's do it general.
You have a condition between M and K, right?
I'll say. Right, yeah, we'll get to that. So a priori. For these, the only thing we can do, we can incorporate one into one of these guys, right? We can get an M1, but that's the only one, and the other ones are just gonna be at this vertex only, so we get a multi-partition of the rest, K minus M. But in this case, here though. What we have is that, so if you have a dimension, but if you have a representation of dimension, just it's called just A0. So there's nothing here, just something only here. Then it's the zero representation. Right. In other words, the transformations all act by zero. So it's so to be simple, so it's simple. If and only if A is equal to just one. So if A were not equal to one, since there's nothing acting, it's like a trivial group acting on a vector space. It decomposes into as a sum of simple representations of dimension one. That's what's happening here. There's nothing acting, so it's just decomposing into ones. So we're not allowed to have a general multi-partition. We're only allowed to use simple representations. I think that the sigma corresponded to the simple dimensions. So really, it just has to be only one. So we could have a priori some dimension one times 1 0 plus dimension k times 1 0, or not k, but say L, where d1 plus dl equal to k minus n. That we could have it just like this, we're only allowing ones. But now the other problem is that even if you have a representation of dimension one, it's zero. So you can't have two different representations of dimension one in this case, there's no loop. But in fact, you're not even allowed to have this, you just have to have k minus n times 1 0. It's the only possibility. The leaves, I guess, how you do this? The leaves are just labeled by just this one number, and the rest of it, you can only allow to have so everything else is just zero, a bunch of copies of a one-dimensional zero representation. So now, what is a leaf isomorphic to? So this leaf is isomorphic. Each leaf, the leaf closure, is just isomorphic to the quiver variety for the smaller leaf. Just instead of using K, use M. So each of the leaves here is isomorphic to another variety of the same quiver, but just with smaller K. This leaf. So all the leaves are given by just varying this K. And when K is when you get down to 0, you just get this one off on its own, you get a point.
And what is the dependence of slicing?
Yeah, so for the slides, yes, I'm just describing the leaves,
Also the dimension.
Yeah, the dimension, so let's compute the dimension. The dimension of this guy, of each of the leaves, it's equal to dimension. Yes, so we're going to have to probably make an assumption here. Let's assume that n is bigger than 1, probably. Or you want to do the n equals 1 case as well?
It seems to
Okay, yeah. What do you mean?
otherwise. If you only consider the that's the view for
Well, let's just start out with n greater than 1 and we'll see what happens if n is not smaller than k.
Yeah.
So the dimension of this leaf, then it's going to be a dimension of this variety, which is the expected dimension, which is 2 minus this m1 the cell. Which is the 2 minus, and that this guy is gonna be 2m squared minus 2mn plus 2. Right, so then this cancels, we get 2m times n minus n. But not the same right there. Okay. Right, so the m needs to be bigger than f, just say.
Otherwise, we have to be stubborn.
Right, this, yes, the point is that, the point is, yeah, so the point is that, right, yes, this is the point, I can tell you what the point is. Stabilizers, yeah, actually, the point, it's slightly different than that, so. So I just say. So if we're bigger. Or no. Again, by fully open. If alpha is not sigma. There exists a canonical. Alpha is a sum of alpha 1, alpha m, where these are all in sigma. And m isomorphic to the varieties for each of the alphas. But now the point is that if we take this quiver A and 1, so if K is bigger than n, then we get that. The file is called a function, and we get that m0, 0 K1 actually has spark to m0, 0 A minus n. So we can get rid of one of those and it is what's called a reflection. Yeah, let's go to the lens. 1 second. Sorry. This would be if we use a stability condition. So with the 0 stability condition, yeah, it's gonna be, yeah, sorry, it's gonna get you down to I think, yeah, probably down to, so if n is equal to k, then this is all right, then, right? So I think it would be n.
Maybe you want to say K equals to.
Yeah. We do n one.
Singular case. So for the singular case, you can put the thing.
Yeah, so what happens is that, but I'm trying to do this too fast. But what happens is that, if you have something bigger than n, then a representation decomposes as n1 plus the rest. So therefore, we just get this item. These are all the zero representations. So we get this isomorphism. We can put it down to n. K is bigger than n. This is what happens. So you could have k bigger than n, but this isn't going to add anything. So the dimension vector, the expected dimension will only be correct when k is less than or equal to. So you could have n greater than or equal to k. It's still be okay. Is that right? Oh, so you wanted k to be down to a half. Do this computation. Okay, let me do the computation over here.
What do you want to do with the fund? Do you want to do
Yeah, we should stop, yeah, and get lunch. Although I won't, I have to teach after this. So just say very quickly here, but about this thing, to the point is that. You said, I have to go teach it at 1.
what?
So
We don't have much.
we don't have much time. But so I just say, what I was saying here and then I'll stop. So the expected dimension. So 1/2 expected dimension. P of M1. But this is equal to 2m n minus m. This is max. Maximize the decomposition P of m. P of m prime 1 for m prime equal to n over 2. Let's say. We can maximize this dimension here when m is n over 2. So it's just maximize, it's a maximum. M over 2. So this says that, if you take an n1 is in sigma, implies that n is less than or equal to m over 2. Yes, you can have the camera. Does that make sense? So, but otherwise, we would have that the n1 is equal to m over 2, 1, if n over 2. Sorry, it's not very clear. This is, otherwise it's going to be equal to n over 2 plus m minus n over 2, 0. And this is going to be smaller. Okay, so this is the one. So to be in sigma, it need to be less equal to n over 2. So the only thing to allow the decomposition have n over 2, 1 or less. So that's why we got this form then. And then of course for m less than or equal to n over 2, then we're going to get something positive. Okay, so we're only going to have these leaves for m less than or equal to n over 2. So you can do a general m this way, and k, but it's equivalent to doing it this way. In fact, for our purposes, it's enough to take it at most n over 2. Sorry about that. Okay, so let's get lunch then.
We'll go back here,
Yeah, we can come back here.
There is the,
Yeah, so the thing is, I think from the mathematical point of view, it doesn't matter what this k is, as long as it's, you can make it equivalent to being less than or equal to n over 2. But you're still getting pretty cool. It makes a difference to get it bigger. So if you want to vary stability, then that will have some meaning, I guess, if
yes,
k is bigger than n over 2.
yeah, I mean,
Right, so from the point of view of zero stability, just like you get the same thing, whatever k is, if it's bigger than or equal to n over 2. But if you vary stability, then you can, then the expected dimension becomes the actual dimension after you vary stability. So then as long as the dimension is positive or non-negative at least, then you could get something on it. So what's gonna happen then is if you vary stability, then you get a smaller dimension thing, sorry, a bigger dimension, or a product that's big, it's large.